Hello, hello, hello. 1, 2, 3, check. Hello, hello. Yeah. So, so, a very good evening to everyone. Welcome to today's live interactive session on geosynthetics and reinforced soil structures. In today's session, we are going to discuss about the filtration, how to design for filtration and drainage. So these two things we will be discussing in today's session. So if you remember, we had discussed many of the uses of geosynthetics, right? So some uses we already discussed in detail. Those were mainly based on the use as a reinforcement, right? So geosynthetic used as a reinforcement. So those things we actually discussed in detail, right? Detail. Now we will be discussing on some other usage, that is filtration and drainage. So these two are very closely related, okay, closely related functions for which we use geosynthetics, right? So we will be discussing this today, uh, the use of geosynthetics for filtration and for drainage, and in the next class we will be discussing how geosynthetics are used as erosion control structures. Okay, how they are used as erosion control structures for erosion control, and there also will be solving some easy problems regarding to this filtration and something like that. And in the last class, we will be solving how geosynthetics are used as liners for, say, waste management in landfills. Okay, so geosynthetics such as geomembranes, are used as membranes. Geomembranes are used as a lining material in in landfills. So all those things we will be seeing in the last 12th session, and we will be having one more 13th session, and in the 13th session we will be actually discussing how to uh, what to say, how to actually use geosynthetics in all the different aspects. Okay, we'll be just revising everything from first week to 12th week. All the usage aspects, whatever we have studied, we will be discussing those things, revising in 1 hour in the 13th discussion session. All right. So let us start the discussion session slowly. So we'll be discussing some theories and some aspects of filtration and drainage, and then we will be side by side. What we will be doing is that we will be solving some problems regarding these topics. Okay. So side by side, what we will be doing, we will be solving some problems. So let us start. Okay. So what is filtration? Okay, what is filtration? Filtration is nothing but you are preventing something to pass through it, and you are allowing some other thing to pass. Okay, so filtration is what? You are providing a barrier to something, but you are providing passage to some other thing. That is what filtration is, right? So equilibrium soil to geotextile system that allows for adequate liquid flow with limited soil loss across the plane of the geotextile over a service lifetime compatible with the application under consideration. Okay, so that means what? That means that the geotextile system should actually allow adequate liquid, that is water, okay, liquid to pass through it, but it should restrict the passage of soil. Okay, so the main use of this filter is to prevent the passage of soil through it, but allowing easy passage of liquid. Okay, and this activity, this function that it is doing, that it is allowing the passage of liquid and preventing the passage of soil, this that this that geotextile, whatever geotextile or whatever filter you are using, that should be chosen. Okay, it will be chosen in such a way that it does this job throughout the whole service life. Okay, throughout the whole service life. Now, what are the filter functions? Okay, what are the main functions of the filter? Retain particles of the base soil to be filtered, avoid piping, avoid free flow of water. All right, avoid free flow of water. Then survive the construction environmental stresses. Okay, well, these are the main filter functions. Okay, that is retain particles of the base soil that is to be filtered, avoid piping loss, that is it should not allow the fine particles to pipe out, to lose out, and it should allow free flow of water. Okay. Also, it should, when it is doing this thing, the filter should actually avoid getting clogged. Okay, avoid getting clogged, and it should survive the construction environmental stresses. So while it is being placed during the construction, the whatever filter you are using, that filter should actually survive the stresses that come into play while during the construction process, right? And also it should actually survive the environmental stresses. Okay, all right. Now, what are the basic soil parameters? Okay, so we are using a filter for a certain soil, right? We are using the filter for a certain soil. So actually, some parameters about the soil we should know. So the main thing we should, some of the main important things that we should know about the soil. First is your soil classification. What type of soil exists? There is a clay, sand, or silty sand, whatever. What is the type of soil in which you are going to put the filter? Okay, so that you should actually know. What is the type of soil, right? It is the first thing. You should know what is the type of soil, correct? Then you need to know the grain size distribution of the soil. Okay, some parameters related to the grain size distribution. So that is the D60, the D10 size, the T30 size. So with that you can find out the CU1, the coefficient of uniformity, and the coefficient of curvature. Okay, so you can say whether the soil is well graded or poor. All right. So these are the some of the basic parameters of the soil that you should know where you are going to use your filter. The soil type, right? And the grain size distribution. All right. All right. Okay. Okay. Now, the water flow from base soil through the filter should not result in loss of fines from the soil, or if any fines particles pass through, they should not clog the filter during the lifetime. So we have a filter. Okay, we are placing a filter somewhere. This filter should actually prevent the passage of fine particles, soil. Okay, fine soil particles. So what happens generally if the filter is not properly designed? Okay, if the filter is not properly designed, what happens? Fine soil particles actually start passing. Okay, fine soil particles actually start getting lost. Okay, it starts passing through the filter and it is lost. Okay, okay. And this phenomenon is actually aggregative phenomenon. What happens? This piping once this piping starts to occur, it continues until the whole this soil fails. The whole structure fails. So it should prevent this part. And the second thing is that this fine particles are going to enter the filter, right? Okay, these fine particles, they should not actually clog the pores of the filter. Okay, these fine particles should not actually clog the pores of the filter during the lifetime. Okay, these fine particles should not actually clog the pores of the, all right. So if the fine particles clogs the pore, what will happen? The water won't be able to pass easily. So high hydraulic pressure will be generated at that end. High uplift pressure, say you're using some filter at the end of a dam, the high uplift pressures will be generated there. Right. So this fine particle should not actually clog the pores of our filter. Why should not shouldn't clog? So if the pores get clogged, water won't be able to pass easily. Okay, so water won't be able to pass through it easy. All right. The permeability of the filter should be high, right? Obviously, the permeability of the filter should be high. So if the permeability of the filter isn't high, it won't be able to allow adequate uh, loss of water head, hydraulic head through it. Okay, if the permeability of the filter is not high, it won't be able to allow the dissipation of hydraulic head through it. It won't be able to allow the passage of water through it. Okay, the easy passage of water. That's why the permeability should actually be high. Okay. Next is there are many criteria. So there are several criteria given by different courts by different researchers. All of them have given many criteria. Okay, all of the researchers, all of many researchers, many codes have given many criterias on how to choose the uh, perfect filter. Okay, how to choose a perfect filter for a certain type of soil. Okay, so many researchers and many codes have given many criteria. So some of the most common criteria are actually given. So generally there are two criteria. One is the retention criteria and then the other is the permeability criteria. Okay. So you can see one of the retention criteria is given here where D15 of the filter divided by D85 of the soil should be less than equal to 5. So this is to prevent the piping of the soil. This is the it is to prevent the loss of soil particles through it. It is the retention criteria. It means if you satisfy this criteria, you will be able to retain the soil properly. The second criteria is the permeability criteria. Here you can see D15 filter by D15 soil should be greater than 5 to 20. Okay. So what the permeability is criteria actually ensures? The permeability criteria actually ensures that there is adequate flow of water. The soil particles will not, okay, the soil particles will not actually clog the pores of the filter, and there will be adequate flow of water to the filter. Okay, so this is the permeability. All right. All right. Now, one more note is given here. In most cases, it is not possible to directly satisfy the above criteria. In such cases, graded filters are provided. That is, layers of different size soil particles gradually increasing in size away from the base. Okay. In most cases, it is not possible to directly satisfy the above criteria. In such cases, the graded filters are provided. It is different layers of different size soil particles gradually increasing in size. So these criteria which is given here, these two criteria are actually related to soil filters. Okay, we can actually make filter with certain soil layers. So those type of filters are actually the criteria for those filters are actually given here. Okay, so sometimes what we have to do is that we have to give your graded filters. Okay, so layers of different soil particles, okay, in increasing size A1. So say this is the base soil. Okay, this is the base soil, and the loss of this we have to prevent. So here it will be fine. There will be little bit larger particles and little larger particles and little larger. So like this graded filter we can make with the soil layers. Okay. So as I said, there you can make filters with aggregate, right? With coarse aggregate you can make filters with coarse aggregate. Those are soil filters, and also either you can use those filters or you can use geosynthetic filters. Okay, so now what are the basic differences between these conventional filters? It's the filters made up of aggregate and the filters made up of geosynthetic. Those are given. The thickness, generally see you have to use a high thickness of aggregate filters if we are using. So we will be putting some aggregate, soil aggregate, right? Like this. So this thickness of the layer which you have to provide, it's quite high, greater than 150. Okay, and if you're using geosynthetic, just a layer of geosynthetic, say geotextile, will actually serve the purpose, right? So the thickness is very small. Next comes the porosity. The geosynthetic obviously is higher porosity. Tensile strength, this is soil, so this doesn't have any tensile strength. But as you know, this geotextile layer which you will be providing, this will have some tensile strength. You can choose any geotextile as per your choice. Compressibility is very low. This doesn't compress actually, with means the this thickness is not dependent upon the vertical pressure, but this geosynthetic, as this thickness is very small, this is highly sensitive to vertical pressure or normal pressure. Okay, as the geosynthetic thickness is very small, it is highly sensitive to normal pressure. So if the pressure is high, what will happen? This will affect the properties of the geosynthetic. Okay, it will affect the filter properties or the drainage property of the geosynthetic. So that we need to consider. And what about the availability? So it depends upon query. So this, for if you want to construct aggregate filters, for that it will depend, the availability will actually depend upon what means what kind of query do you have surrounding that place, surrounding the site. It will depend upon the availability of aggregate surrounding that site. But for geosynthetic, actually this is not the case. You can manufacture and you can procure any geosynthetic as per your demand. Okay, and these are manufactured in controlled conditions in the factory. So you can procure any geosynthetic as per your demand. Then we have capillary rise. So capillary rise is significant in the soils and for geosynthetic results. And for risk of damage during installation, so these soils, these are no risk of damage. But for geosynthetics, geotextile, these are very delicate structures, right? So you might actually damage the geosynthetic while placing it. You might puncture it, you might rupture it while placing. So there is a risk, a certain amount of risk involved during the installation. So that you need to be very careful about. Okay, you need to be very careful about that thing. So during the installation process, we need to be very careful how we are placing the geosynthetic. Okay, how you are placing the geosynthetic, in what conditions you are placing the geosynthetic. So that we need to be very careful about. Okay, because there is a high risk of damage. Now these were the main differences. Now what are the similarities between these two conventional aggregate filters and geosynthetic filters? Internal clogging by finer particles. So in both cases, fine particles may enter into the pores and they may clog the filter. Okay, they may clog the filter. Then we have biological clogging. Biological clogging means what? There is a certain amount of algae or something like that which grow, and they grow and they can actually clog the pores of the filters. And also there might be some chemical changes through the soil. They might also clog the pores. Then you have clogging due to precipitation of soil. So if you are using it in an alkaline environment, there might be precipitation of salts which will be actually get deposited into the pores, and this will clog the pores of the filter. This can happen in both the cases. Clogging in environmental applications basically, and frost susceptibility. That means if you are uh, using the filters in sub-zero temperature, freezing temperatures, in that case there might be problem. Generally, for filter, okay, for filtration uses, generally for filtration uses, this geotextiles are generally used. Okay, geotextiles are the most commonly used geosynthetic material for filtration. Okay, for filtering, to be designed as a to be used as a filter. So generally, geotextiles are used for filters. So the most important property of a geotextile that you should know to be used as a filter is this aperture opening size. Okay, you already know this term. We already discussed this term before. So this aperture opening size, the 090 and 95 size, this actually we should know. So here a typical data for a tricycle on a woven geotextile is given 090 and 095. Okay, you know how this 090 and 95 are actually found out. So we actually sieve dry glass beads through the geotextile and find out this size, right? 090 is actually the aperture. Now we are while discussing the previous slides, we are continuously speaking about clogging, right? So we were continuously speaking about clogging. So what is clogging? So filling up of the voids in the textile with solid particles progressively until the passage of water is slowed down. This is clogging. Okay, filling up of the voids in the textile with solid particles progressively until the passage of water is slowed down. So what happens as water starts to flow little by little, soil starts to get deposited into the pores of the filter, and the time comes when the passage of the water is significantly slowed down. Okay, the flow of water is significantly reduced. At that time we say that the system is clogged, the filter is clogged, right? What happens? The clogging reduces the hydraulic conductivity, obviously. Okay, and we also can have internal clogging. Okay, this was the external clogging, then we can have the internal clogging. The internal clogging happens due to the mineral particles or precipitation, chemical deposition of particles from the soil to the water, while biological growth, all these things, this internal clogging can also happen. So one clogging is due to the deposition of the fine soil particles, and the other clogging that happens is due to the chemical and biological effect. Okay, chemical and biological effect, it is the deposition of soil particles by biological growth, all these things. Okay, clogging can happen due to these two reasons. One due to the soil particles, another due to these other factors, that is mineral particles and chemical biological deposition. Okay. Now, as I said, there are several criteria. Okay, there are several criteria. How we can select a particular geotextile as a filter. Okay, there are many criteria. So these criteria actually vary code to code, researcher to researcher, and actually what happens is that it's very difficult. Okay, it's very difficult to give some universal criteria which can work in all cases. Okay, because there are many factors which affect this thing. So it is very difficult to give a universal criteria which will work for all cases. Okay, so uh, uh, as I was saying, it is very difficult to give a universal criteria. So still, let us see some of the available criteria. Let us see what are they. So one you can see here. The left side we have geotextile selection for granular soils, and on the right side for clay soils. So here you can see one is the being limit, other is the vulnerability limit. Okay. So for granular soils, O90 should be less than equal to the uh, D85 of the soil, and the permeability, for permeability limit, the O90 should be greater than equal to the D15 of the soil, and also it should be greater than 0.05. Okay. Well, what is O90? O90 is nothing but the aperture opening size, AOS. Sorry, apparent opening size. Sorry, not aperture opening size, apparent opening size, AOS. Okay, that is O90. O90 is what? Apparent opening size. So, so we are discussing here, right? Apparent opening size. This is apparent opening size. This is O90. Okay, this is the apparent opening size. But there are many criteria actually given. So you can see for granular soil is different, for clay soil is different, and then below if you see there are certain more permeability criteria given. Okay, this O95, let's say 75 micron, flow rate required it should be equal to 30 liters per meter square per second, 100 mm head. There are several criteria. Okay, so you need to judiciously choose which geotextile you want to use for your soil and for that particular purpose. Very useful. Okay. So you can see here some of the permeability criteria given by Giraud. So for granular filters, the K of granular filter, that is the coefficient of permeability. K. The coefficient of permeability K for granular filter should be greater than equal to 10 times that of the soil. Okay. And for geotextile filter, the KAG for geotextile filter should be greater than equal to 0.1 Ks. As Tg is the T, there's the thickness of geotextile is almost 1 by 100th of the thickness of this GS. This is the granular soil. Okay. So here you can see some more guidelines. These are known as the German guidelines. So here German they have defined the criteria based on types of soil, and these types of soils are stable soil. Okay, stable soil, unstable soil, problem soil. These types. So what are stable soil? Stable soils are soils with uniform gradation or linearly graded broad gradation soils. It is well graded soils. Okay, so uniformly graded or broad or well graded soils. Those are stable soils. Okay, uniformly graded means what are uniformly graded? So this uniformly graded is well graded. Uh, how will you get to know that the soil is uniformly graded or well graded? You can know this from your grain size distribution. Okay, the grain size distribution of the soil. Okay, so the soils are stable which are uniformly graded or well graded. Well graded means equal portions of all sizes of particles are present. Okay, all particles is are present in the soil. And what is uniform graded? Uniform graded means soil particles have a uniform size. What is gap graded? Gap graded means gap graded soil. Unstable soils are actually gap graded soil. These gap graded soils are those soils where this say only some sizes of soil particles are there. Okay, they are missing the, say you have only some particle size, then you don't have other, then you have other particles like that. Okay, so these are gap weighted soils because many particle sizes are missing in the soil. In that case, what happens, that there is no free internal movement of the soil. Okay, so stable soils are well graded or uniformly graded soils, unstable soils are gap weighted soils. Now what are the German guidelines? So if the soil's D40 is less than 0.06 mm and it's a stable soil, then the geotextile, the apparent opening size from the wet sieves test should be less than 10 of D50, and DW also should be greater than 2 of D90. These two criteria it should follow. So these four criteria are given for stable and problem soil. Okay, and varying the D40 sizes. Okay. So more description about the problem soils are given here in the below. Here you can see fine grained soils with the plasticity index less than 0.15, soils whose D50 lies between 0.02 and 0.1 mm, soils with a uniformity coefficient less than 15, it also contains grains. Okay, so as I said, there are many criteria, and these are only some of the criteria. Okay, some of the criteria. Just give me a second. Okay, just a second now. Yeah, yeah. So yeah, so let us see this basic easy problem. For a particular soil, D10 is 0.03 mm, D50 is 0.07 mm, D60 is 0.09 mm, and D90 is 0.25 mm. Okay, so we need to select a suitable geotextile for filtration by German. Okay, so what is the D50 size here? The D50 size is 0.07 mm, right? The D50 size is 0.07 mm. Let us see. Now D50 should actually lie between what? Point. If the D50 lies between 0.02 and 0.1 mm, that means what? The soil is a problem soil, right? So here, if this is the case, then the soil is a problem soil. Okay, and what is our D50? 0.07. Okay, Now let us find out the coefficient of uniformity. T60 03 is equal to 3 is less than 15. Okay. Therefore, TW should be less than 5 to come out as 26 and 20. Okay. Therefore, GW should be less than 0.2. Now, what is gradient? So, we studied this gradient ratio test before also, right? We had gone through this gradient ratio test before also. If you remember, we had discussed in detail. So, now we won't be discussing this detail. So, this gradient ratio test is actually used. This gradient ratio test is actually used to understand or to establish the see the if a soil and a geotextile are compatible. Okay, to understand the compatibility between the soil and the geotextile. So that's why this gradient ratio test is used. So what we do is that we measure the heads at this at different points, and we try to determine this gradient ratio. Okay, so try to determine this gradient ratio, and so what happens is that as time passes, the gradient ratio actually increases, and then it actually becomes constant. That means this steady state has been established. Okay, that means that the steady state has been established. Okay, so if you see these two figures here on the rightmost side, so we can see that initially that is unstable. Okay, initially this is unstable, so you can see the system permeability actually reducing to some constant, obviously, because as the water starts to flow, the soil particles will get readjusted, some soil particles will get entered, uh, uh, will form a bridging. There will be some bridging of soil particles around the pores. All these things will happen, so that is the unstable condition. So there is automatic soil filter formation around the geotextile. Okay, that happens in the first stage. So what happens, the permeability slightly reduces, and then after this equilibrium is established with increasing time, you can see that the system permeability actually goes constant. Okay, and initially what you can see that the weight of the piped soil particles initially it's very high, then it start to reduce, and then as the soil filter is formed, as the equilibrium is established between the soil and the geotextile, what happens, the weight of the weight of the soil piped will actually reduce to almost zero. Okay, so like this actually we need to do some tests and establish the compatibility between the geotextile and your this soil, right? Now let us solve some problems. First, let us solve some problems regarding this filtration. Okay, so let us see the problem. Given a 3.5-meter high gabion wall consists of 1 into 1 meter into 1 meter into 3 meter long basket sitting on 0.5 meter into 2 meter into 3 meter long mattresses shown. The backfill soil is a medium density sand of D10 this much, coefficient of uniformity 2.5, D85.1 mm, coefficient of permeability is given, and relative density of 70%. Okay, check the adequacy of three candidate geotextiles whose laboratory test properties are given below. Use a cumulative reduction factor of 15 in order to adjust the ultimate laboratory obtained permittivity value to a allowable field of view. Okay, so you can see three geotextile are given here: non-volatile funds, fluid monofilament, and non-volatile fund. Permittivity of all these are given, and the apparent opening size is also given. So first, what we need to do, the first step is to calculate the permittivity. Okay, that is the first step. Okay, the first step is to calculate the permittivity. Now, what is Q? This is the first. Now, what is the flow rate Q? The flow rate Q is nothing but, if you know from the soil mechanics, basic soil mechanics, for the seepage chapter, KHF by N. Where K is the coefficient of permeability, H is the air loss, F is the number of flow lines, and N is the number of potential drops. So what we do, say we have like this, we have an arrangement. So what we need to do is that we need to construct the flow lines and the equipotential lines, and we need to construct the, okay, we need to construct the what? You need to construct the flow net. Okay, so you need to actually construct the flow net. Okay, from this flow net, if you see what are the number of flow lines, what are the how many flow lines are there? 1, 2, 3, 4, 5, right? So sorry, this na, or how, so let us first see how many number of potential drops are there. 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. 5 number of equipotential drops, and approximate number of flow channels. If you see how many, 1, 2, 3, 4. Right. So these are the equipotential lines, and these are my flow lines. Right. So 1, 2, 3, 4 flow channels, and 1, 2, 3. Here to here 1 drop, 2 drop, 3 drop, 4 drop, 5 drop. Okay, total 5 drops. Right. So what we can do? then write K H and F by N. So what, how much was K? K for the soil 0075 meter per second, 0.0075 into total head loss 3.5 meter. Okay. So let us see how much this comes. Done. Next, what we need to do, we need to calculate the required permittivity. Okay. So Q is KIA, right? K into head loss by T to A. So what is why this is K by T equal to Q A, right? What is the flow? And this is happening through 3.5 meter into 1. 3.5. What is the area? 3.5 into 1. So 3.5 into 1 means this 3.5 height into 1 meter along this direction, out of plane direction, 1 meter. Okay, so 3.5 into 1. From here we will get 1.71 into 10 to the power minus 3. Okay, now we have 3 geotextile, right? We have three number of geotextiles here. So for each of these geotextile, we need to actually find out the factor of safety now. Okay, so GTX1, GTX2, GTX3, right? What is the ultimate values? Ultimate for first one is 2, 1.2 and 0.4. This 2 ultimate equal to 1.2, ultimate equal to 0.4, right? Right? Then these need to be actually converted to allowable values. So phi allowable is equal to phi ultimate times 1 by certain reduction factors. Reduction factors for chemical, this biological clogging, then reduction factor for creep, then reduction factor for intrusion. Like this, many reduction factors are there. Okay, there are many reduction factors. I will tell you. So creep, intrusion, chemical clogging, and this one is what? Biological clogging. Okay, CR is creep, IN is intrusion, CC is your chemical clogging, and BC is your biological clogging. These are certain reduction factors. So if you then do, can be to combined, you can take say 15 cumulative, this one you can take 15. So that from here this LIable will come out as 0.13, 0.08, 0.027. Okay, so therefore if you want to find out the factor of safety now factor of safety is nothing but Q allowable by this one required. So Q allowable by what is the required? 1.71 into 10 to the power minus 3. So we found out for geotextile 1.13 divided by 71 into 10 to the power minus 3, 76 to 47. So all are actually acceptable. Okay, so all are actually acceptable. This is for your this flow criteria. Okay, flow criteria. Now the second part of the design, okay, the second part of the design is related to our retention criteria. Okay, the second part of the design is actually related to our retention criteria. Okay, second part of the design is actually based on the retention criteria. So there are many criteria available. So out of that, actually for this problem, corner in Adam corner, so they have used the Carroll's criterion. Okay, this says that the O95 should be less than 2.5 times D85. Okay, that is O95 should be less than 2.5 times 0.15 less than 0.37. Right? Let us see for first geotextile. See, for first geotextile, aperture apparent opening size is 0.30 mm. It is less than 0.375. Second one is not acceptable. It is not less than, and third one is acceptable. It is less than 3. So candidate geotextile 1 and 3 are accept. Okay, so both are okay. Now let us see one more problem. Design a geotextile filter surrounding an open graded stone aggregate that in turn surrounds a perforated pipe under drain and from the sketch below. So here you can see you have a perforated pipe under drain, then you have crushed stone over it, and surrounding that you have geotextile. Okay. Flow will enter through the stone base. So you have CR 450 mm thickness stone base is there. So water will enter through the stone base from the upper part of the under drain, while soil infiltration will come from the surrounding native soil. Okay, so water has to enter from the stone base, and this and the soils upgrade. The soils upgrade the soil. This soil might actually enter into the filter. Okay, the soil is a dense in the sand with 11 properties. All properties are given here. The geotextile being considered is a non-movement needle punched with laboratory tested values of permittivity and apparent opening size. Okay, so we need to choose a geotextile that we can use a filter here that can allow adequate passage. Okay, that can allow adequate passage of water from the stone base into the under drain, and it also has to stop the surrounding separate soil to intrude into the filter, intrude into the geotextile, or intrude into the under drain block clog. Okay, so again we will calculate this similarly. So for these type of problems, the first thing that we need to choose is actually the what is the amount of flow that might be taking place. Okay, so here in the corners book, actually they have selected a certain amount. I will write that 15 meter cube day. Okay, this is the total amount of flow, maximum amount of flow that might be coming. Okay. Second is the calculate the required permittivity. So again, you know, Q is equal to KIA. Point 0.45 is that because the total this flow will be actually occurring across this 450 mm. So 0.45 times area. What is the area? Area is 0.3, 300 mm, 0.3 meters into 1 is per meter out of print direction per meter length. So 0.3 into 1. So this will come out as 111 T inverse is equal to approximately 1.3 into 10 to the power minus 3 second inverse. So day inverse means 111 divided by 3600 into 24. Okay, divided by 3600 into 24. It comes out as 1.28. So approximately you can take 1.3 into 10 to the power minus 3 second inverse just for so that our divide remains conservative. Okay. Now we need to find out the allowable permittivity from the ultimate permittivity. Okay. So what is the ultimate permittivity? It's given 1.5 second inverse and aperture operating size is 0.212 that will be needing in the next part. So 1.5. So to choose these values, actually many tables are available in the literature. So I will be showing you one table later so that you can refer. So many tables are available. Right, this will come out as the factor of safety for flow, allowable, required, so 0.058 divided by 1.3 into 10 to the power minus 3 45, approximately 45. So accepted. Okay, the next part what we need to do is, we need to design to check for the filter retention criteria. Right. So as I said, there are many retention criteria that are given by many researchers, many codes. And so none of them actually work in all the cases. Right. You cannot say that this will work in. So that you need to use very judicious. Right. So this is one soil retention criteria chart. It is given in Corner's book based upon literature et al. So here you can see there are many criteria given. Okay, so there are many criteria given from which we can actually select the appropriate criteria that is necessary for us. Okay, from here actually we might select the appropriate criteria which might be actually appropriate for us. Okay, this is one of the charts. Okay, like this many charts are available from where we can choose the required criteria. Okay. So let us see. So for R case U is 5, RD is actually 80%, right? And D50 is 0.035. Relative density is 80%. U is 5. So you can see here as U is greater than 3. Our U is 5. Okay, C is greater than 3. And RD is how much? 80%, I guess. 80%. So it's dense. So what we can do, we can select this criteria. Okay, we can select this O95 less than 18 by CU D50. Okay, so ID for dense for greater than 65% and CU is widely graded. It is CU is greater than our CU is 5. Here CU is greater than 3. It is 5. So we can actually select this criteria from here. Okay. Therefore, if we take this O95 required is less than 18 by CUT50 less than 18 by 5 into 0.035 would be less than 0.126. But but you can see the candidate geotextile that is given here, that has a opening size of how much, 0.212 mm. So this actually does not does not satisfy the criteria. Okay, this does not actually satisfy the criteria. So 0.212, sorry, 0.212 actually not less than just the current geotextile in consideration. um, so we need to use some array. So you cannot use the current geotextile that you are actually thinking to use. That we cannot use. So you need to use some other geotextile that is little bit tighter, where the pores are little bit more smaller. Okay, that is actually quite possible. We can find the one more this one. So this vector of safety in flow might reduce a bit. It's very high, 45, so it might reduce a bit, but then we can satisfy the other criteria also. So both the flow criteria and the retention criteria both should be satisfied. Okay. Next, let us come to drainage. Okay, so now whatever you studied, it was what? Cross plane flow. Okay, regarding the cross plane flow, where the water was flowing like this. So this is the geotextile, this is the geotextile, and water was flowing like this. This cross plane flow we are studying. Okay, so we are studying the cross plane flow. Now whatever we will be studying, that is related to the in plane flow, that is the drainage in plane flow. For the filtration, this cross plane flow or the permittivity is important, right? But for the drainage purposes, the in plane flow, that is the in plane flow, that is the transmissivity. Okay, the in plane flow, the flow across the plane of the flow across the plane of the geotextile, that is important, not the cross plane flow. The cross plane flow is important in filter section, but now for drainage is in plane flow is actually important, right? So generally what happens, generally we have a pavement, right? Pavement, and below we have a subgrade. So if soil enters into the subgrade, it will be very difficult because it will generate pore pressures this when vehicles are moving above it, and this will actually damage the pavement. That's why what we need to ensure is whatever water is actually falling to the pavement, it goes and drains out immediately. It should not enter the soil subgrade. Okay, so for that, this geotextile is used as a drainage. Okay, there are many other uses of drainage. So you can see there are many applications, drainage applications which are mentioned. So pavement edge drains. So we already discussed about pavement edge drains. Interceptor trenches on slopes. So say you have a canal. Okay, canal. You have a canal. Okay, we have a canal. Okay, water actually flows through there. You have a canal, and what we can do. So we don't want that any water seeping out of the canal to come into the soil here, okay, to flow into the soil. So what we do, we make a trench, and there we put geotextile so that this water is actually gets intercepted. Okay, So water actually gets intercepted. Then we have drainage when apartments and retaining structures. So behind retaining structures, retaining walls, we generally use geotextiles so that the water is drained out. The water is drained out, and if the water is not drained out, what will happen? We discussed this in the initial lectures also. If the water is not drained out, there will be extra hydrostatic forces that will be acting, and due to that, the structure might fail. So it's very important for us to. It is very important for us to drain the water out. Okay, it's very important for us to treat the water. Then we have relief on water pressure body structures, substitute for conventional drains, Richard collection and gas venting, drainage mats in horizontal applications, improving PVDs for accelerated consolidation of clays. This already we studied. So there are many such uses where geotextiles or geosynthetics are used as drainage. So apart from geotextile, one more important geosynthetic that is used for drainage application. So can you name that? What is one more important uh, geosynthetic that is actually used for drainage application? Can you name that thing? What is the one more? Okay, what is one more uh, geosynthetic that is used for drainage application apart from geotextile? Very important. Whose only purpose, the main purpose of that geosynthetics is drainage. If you remember, that is what? Geonet. Right, that is geonet. So geonets are actually uh, regularly used. Okay, geonets are actually used for this drainage applications. Okay, so generally what happens in drainage applications, there we have a core. I mean core is there, core of geosynthetic material. This core actually helps in the drainage of the flow of water through it. Okay, that core actually carries the water through it and aids in the flow of water. Okay, so generally there is a core. Okay, so outer there is some filter covering. Okay, outer filter cover. Inside that we have a core which actually carries the water. So water actually flows through this core. So there are many types of core that are possible. One is the stiff three-dimensional web or mat. So web of this geotextile, geosynthetic material, or we can have extruded set of intersecting ribs. That is that geonets where two planes are there, different planes are there. They actually allow the water to pass through. Single or double cusped sheets that are shown in the figure, raised shrubs or columns, found from three-dimensional boxes across network. So many combinations of this core are possible. This core, what does this core do? This core actually aids the flow of water through it. So aids the drainage. Okay, and surrounding the core we have a geotextile that acts as a filter material. Okay, same as if you remember PVDs. In PVDs we had a plastic corrugated sheet like thing, right, inside, corrugated sheet inside, which actually carries the water through. And surrounding that core we have a surrounding that PVC core, polyvinyl chloride, or the plastic core, we have a geotextile which acts as a filter, right? The same thing. Okay, the same. So as I said, in for drainage, the important thing that is important, most important thing is the transmissivity property that is called as transmissivity. Transmissivity actually defines the in plane flow of water through the geosynthetics. So all the tests regarding all these things we've already discussed in the initial lectures. That's why hence I'm not repeating this again and again. We already discussed this long back. So just here, just for revision, I have given just given again. So in short, I will tell that how these tests are done. So you can see here a geotextile is kept of length L. A certain amount of pressure, vertical pressure is applied. Vertical pressure is applied, or normal pressure is applied, and a head is maintained. Constant head is maintained, and this is the constant head test. Okay. What is the gradient of flow? The water head divided by the length, that is the gradient of flow. So in that gradient of flow I, the water is actually flowing through the geotextile, through the plane of the geotextile. Okay. So the flow is equal to KPIA. KP is the in-plane permeability of the geotextile. So I is the gradient of flow in area. Area of flow. So what will be the area of flow? Say this is the geotextile. This is the geotextile. So what will be the area? So water is flowing like this, right? So this area, this width times the thickness. Width times thickness. In this cross-sectional area, the flow is occurring, right? So width times the thickness. This area, this flow is occurring. That's why W into T. So KIA, KPI, W into T. So Kp into T, this K into T is actually nothing but the transmissivity. Okay, this is nothing but the transmissivity theta, which is denoted as theta. This is equal to Q by I, Q by I into W. W is the width of the geotextile, the width of the sample. Okay, so this is how we do the test and determine the transmissivity of the geotextile. Fine. So as I said, these are the recommended reduction vector value to get the allowable flow rate of geotextiles. Okay, these are given by corner. So as I said, so there are many reduction factors that we used. The first reduction factor is the RFSCB, that is the soil clogging and blinding. Okay, so in various applications we can use various factors. Second is the creep reduction of the voice, then intrusion into the voice, then chemical clogging, then biological clogging. Okay. Okay. These are the suggested values, range of reduction, suggested ranges of reduction factors that you can use. Okay, these are for geotextiles. Then we have this. These are the values for geonets. So in geonets, we do not use this SCB. The only these 4 reduction vectors are used. So here we had 5 reduction vectors, but for the geonets, we use the other 4 these reduction vectors: the intrusion, creep, chemical clogging, and biological clogging. Okay, so in various uses, in various application areas, reduction vectors vary. The approximate value of reduction vector you can get. And generally, the manufacturers also suggest some value. Okay, so the manufacturer from where you will be procuring the procuring the geosynthetic, from there also actually you can get these values. Okay, so now let us see the problem. Yeah, so a 10-meter high zoned earth dam is to be used as an irrigation reservoir with a cross section as shown below. A geotextile is being considered behind the clay core wall as a chimney drain and the drainage gallery. Okay, geotextile under consideration is a 200 gram per meter square. That is the weight per unit area, weight of the geotextile. Non-woven needle punch geotextile with so these non-woven type of geotextile, these are generally very good for drainage purposes. Okay, non-independent geotextile with ultimate transmissivity values of 15 to the power minus 4 meters per meter square per minute. Use a cumulative reduction factor of 8, means the multiplication of all the cumulative factors IN, CR, CC, PC that is given here. It is 3 we have to use. What factor of safety does this geotextile have for the amount of flow seeping through the clay core wall, which is a clay sheet of permeability into the ionosphere? So we have a sound earth dam and 10 just say over 10 meters high. We have a chimney drain. So geotextile is actually provided here. You can see here, and then the geotextile is actually to carry the water. Okay, so the water will actually coming here, right? Coming here, entering like this, and it will go flowing like this and flowing to the drainage gallery outside. Okay, so we need to design this. Alright, so the first task again in this case is to determine the flow, amount of flow that is taking place. Okay, so we have to determine the amount of flow that is taking place. So in order to determine that, what we need to do, we need to actually draw, again you have to know to draw the flow net. Okay, so here you can see a flow net is already drawn here. Okay, flow net is already drawn here. So what are the number of flow channels? You can see 1 2 sorry, extremely sorry, just erase it. 1 2 3 4 5. Okay, flow channels, and what, and this is the equipotential line. So 1 drop, 2 drops. Okay, total 2 drops, total 2 equipotential drops and 5 flow channels. So like this we can, what we can do, we can determine the flow. What is n? Is 10 to the power minus 7. H, what is the head? Head is 10 meters. What is F? Number of flow 5 and number of drops 2. Let's calculate this. It is now in this 10 to the power minus this one is in meter square per second. But in meter square per minute, if you want to find this out, so for minute we need to what, 1.5 into 10 to the power minus 4 meter square per minute. Okay, now what is the gradient of flow? This is very important. What is the gradient of flow? This head loss is according to what? So the see, so the water is actually flowing here, right, along this geotextile. It has to drain along this. So head loss is occurring across this line, the gradient. So what is this head? I, H by L. H is what? Total head. L is the length along. So say here, right? So here. So this is H and this is my L, H by. So this we can write it as sine 75. What is sine 75? H by L. If you consider this is a triangle, If we consider this as a triangle, then this is h, this is l. Okay, so sine 75 is h by l. So if we do sine 75, we can get this I value, right? L is what? L is the length of flow. H is the total head. Hence, the gradient of flow, I can write it as sine 75. So how much is sine 75? Point. Just a second. Just a second, huh? Just a second. Yeah. So we got the gradient of flow. Now what we need to find out? We need to find out the required transmissivity. Okay, we need to calculate the required transmissivity. So what is Q? KIA. KI, thickness into width, right? So KT is what? My theta, I will separate it. I into width. So theta is equal to KT is equal to what? Q by I into width. So what is Q? 1.5 into 10 to the power minus 4 divided by I into I, we already found out 0.97 into width. Width you can consider per meter length. So 1. Yeah. So 0.55 10 to the minus 4 meters square per. Okay. Now vector safety allowed by theta required. Okay. So what is theta allowed? Theta ultimate divided by cumulative of reduction factors required. Vector safety 5 into 10 to the power minus 4. This is given. This is also given. Let's see how much this comes out. This is 50, na? 3.22. Okay, so this comes out as, so generally, this is actually quite low. Generally we require FOS 5 to 10. Okay, then it will require a vector safety of 5 to 10, so it is quite low. So what we can do is, so one option is to change the geotextile, other option is to increase the thickness. So if you increase the thickness of the geotextile, okay, this allowable Q allow, that will actually increase. Okay, that we can do. All right. So this is one factor. Okay, this thing you need to choose. So choose accordingly. Also, after this, what we need to do is that after this, so the soil retention from previous. Okay, so generally like this you can just approximately design, but to get the proper thing, what we do, you need to do a gradient ratio test, and then satisfy the compatibility of the synthetic and the soil. Okay, just a second. Yeah. So this is just retaining wall problem. So with this problem, just you can get an idea, okay, what all uses, okay, in what all uses this is actually this geosynthetic or geosynthetics are actually used. In what all areas these geosynthetics are used as for drainage purposes. Okay, this with these problems that you can actually get an idea. All right. Okay. Let us see the next problem. Just a second. Yeah. So calculate the factor of safety of 500 gram per meter square non-woven needle punch geotextile required to drain water from behind the 8-meter high concrete cantilever heating wall if it has an allowable transmissivity of 0.15 into 10 to the minus meters cube per minute at its maximum design pressure. The soil backfill is a silty sand with K of this much. Okay. So here we have a retaining wall. So as you know, we need to drain the water out of the retaining wall. So all the water that will be here in the backfill, so it will enter into the geotextile drain. It will flow through the geotextile and then come out of the weep hole like this. Okay. So for that purpose, actually, we need to design the drainage. We design this drain. Okay. Okay. Okay, so just give me 1 second. Yeah, sorry for the interruption. Let us start to solve this problem again. Right. So we need to. So here we have a retaining wall, cantilever retaining wall, for which we need to calculate the find out the factor of safety for the mentioned geotextile. All right. So let us again find the flow first, right? So again, as usual, we'll find the flow first. What is Q? KH F by N. For that, we need to draw the flow lines, and for that, flow lines are the flow potential lines, and draw the flow net. And here, the flow net is already given to you. Flow net is actually given to us. So we can see here what are the number of flow lines: 1, 2, 3, 4, 5. It is K, which is it. 1, 1, 2, 3, 4, 5. Drops 1, 2, 3, 4, 5. Right? I think 5 by 5. This number again is 5 by 5. So here we have 5 into 10 to the power minus 5, 8 into 1 is this much meter square per second per minute if you want to do. 0.024 into 60. Okay, to convert it to meter square per minute. What is the gradient? Here it is vertical, so 990. 1. Now transmissibility. Q is equal to KIA K I thickness into width. Theta is equal to KT is equal to Q by I into W. Q is 0.024. I is 1, width is 1. Per meter width we are considering per meter width. So 1, 0.024 meter square per minute. Okay. Therefore, factor of safety. What is factor of safety? Q required, theta required by theta allowable. Theta required is 0.024. What is the theta? Sorry, theta. Sorry. Wrote it opposite, right? Should be theta allowable by theta required. So what is theta allowable? 0.15 into 10 to the power minus 3. 0.15 into 10 to the power minus 3 divided by 0.024. So it comes out as 0.0062, which is not nearly acceptable. Okay, which is not nearly acceptable. It is not acceptable at all. Right? So we need to choose some other your synthetic material, but for this type of problems where there is a little bit higher flow, what we can do is we can go for geonet. Okay, we can use geonet. Okay, whatever be the case, let us see the next problem. So a refrigerated storage building for frozen foods is to be founded on the site illustrated below. A capillary break beneath the building's foundation having a geotextile is being considered as a solution. Will sorry sorry. Yeah. So will a 700 gram per meter square non-woven needle punched geotextile having an allowable transmissivity of 0.0007 meter square per minute at 25 kPa normal stress be adequate if the required factor of safety 3. Given upward flow rate is 2.7 into the power minus 5 meter square per minute. So upward flow rate is given to us. So here see let us see, these are actually showing you all the various uses where we can use the drainage function of a geotextile. So here we have a frozen food storage building where temperature will be less than 0 degrees, right? Okay, refrigeration storage building, and water table is actually downward. So what will happen, due to temperature difference there will be this capillary flow of water. Okay, there is a tendency for the upward capillary flow of water. So what will happen, so if this capillary water actually reaches the bottom of this frozen storage building, the frozen storage building, the temperature there is very less, right? So there are chances that the water will freeze. So if the water reaches there and that water after reaching there gets frozen, what will happen, it will get expand, it will get expanded, and as it expands it will actually damage the structure. Okay, it will actually damage the structure. So as a result, what we need to do, we need to drain out the water before it reaches that place. Okay, we need to drain out, we need to arrest the water, we need to drain out the water beforehand. Okay, so here for that purpose we are using a geotextile that will actually arrest the water and it will drain out the water through the under drains. Okay, the geotextile will catch the water, water will flow through the geotextile and then ultimately drain into the under drains. So the under drains will ultimately carry the water and drain them out. Alright, alright. So this is the main purpose. Okay. You can see here a 5% gradient is there actually for the flow of water. A 5% gradient is there, and water will actually flow along a 5% gradient along the geotextile. Okay. So upward flow rate of the water due to this capillary action is given 2.7 into 10 to the power minus 5 meters square per minute. Okay. Okay. So let us see. This is a very easy problem actually. Everything is given. This directly we need to find out. So the flow Q is 2.7 into 10 to the power minus 5. 5% slope is equal to 0.05 gradient. Calculate the first we need to do what we need to do. We need to calculate the required transmissivity. So again same. What is Q? Gradient is less 0.05 to width 1 per meter width. So let us calculate this. 5.4 into 10 to the power minus 4 meter square per minute. Okay, 5.4 into 10 to the power minus 4 meter square per minute. Now, what is the factor of safety? Required by, sorry, again I made the mistake, allowable by theta required. So what is the allowable? It's given here, allowable transmissivity of 0.007. So actually 1.3 is less than 3, so so at least what we need to do to increase the factor safety, what we can do is we can increase the layers of geotextile. Okay, so we can increase the number of layers, so 3 to 4 layers of the same geotextile we can provide. So what it will do, it will actually increase this theta allowable. Okay, theta allowable will get added up, and this theta allowable will actually increase. All right, so if this theta allowable increases, then it will solve our problems. The thickness will increase, the theta allowable will increase, so factor of safety will increase. So at least one layer of this geotextile won't be sufficient. At least we need to use 3 to 4 layers of the same geotextile. Okay, so 0.0007 to okay, these 3 to 4 layers of this geotextile is required, or what we can do, we can use geonet, okay, in place of geotextile. Okay, next similar problem, determine the drainage factor of safety for the geonet behind the 8-meter retaining wall is shown below. The response curve of the geonet is also given. Response curve means what? The flow rate. The flow rate will change with normal stress. So if normal stress is high, the geonet will actually squeeze. Okay, geonet will actually provide less flow rate, obviously, right? So there is pressure acting on the geonet, so the flow rate will be less. Less tolerable stress, it will give high flow rate. So for our geotextile, this response curve is given here, and what we need to do, we need to actually see how much vertical pressure how much normal stress is actually generated, and corresponding to just that normal stress, we need to choose the flow rate for our geonet. Okay, for our geonet. First again, same we will do when you will find the flow from the flow net. Just write it down. Flow gradient sine 19 because it's vertical, then theta allowable. So what is theta allowable? U by I into W. Again I am not doing the same thing, directly I am writing same, right? Now what is the vertical pressure? So average vertical pressure, average normal stress is nothing but half into, what is the height? Height is 8 and what is the gamma? What is the unit weight? Unit weight you can take, unit weight is 18. Okay, unit weight you can take as 18, half into 8 into 18, assuming gamma 18 kilonewton per meter. So from here you will get half into 8 into 18, average 72 kPa. Okay, from the given response curve for I equal to 1 and normal stress 72 kPa, we get theta this won't be the allowable, right? This will be the ultimate value. Okay, theta ultimate is equal to, so you can see various I values and this normal stress. So almost 72 will get close to 0.1. So let us take 0.94. Okay, So here we will get something like this, right? So we have like something here. So approximately what you can do, you can take 0.94. Ultimate is 0.94 meter square per second per minute, equal to nothing but 50.6 10 to the minus 4 meter square per second. Okay. Just write this unit. So what is the unit? Just see here properly. It's meter cube per minute meter. So meter square per minute. Meter square per minute. So meter square per minute will be 0.94 is 0.94 into 60. Divided by 3600, sorry, 60 seconds. Just a second. 0.094, not 94. Yeah, it's not 0.94, it's 0.094. 0.094. 15.6 10 to the power minus 4 or 1.56 to 10 to the power minus 3 square per second. The ultimate. Now what we need to do, we need to find out the allowable theta ultimate by reduction factors. Reduction factors you can choose accordingly from the table that I had provided you. From there you can accordingly choose. Directly I will write this 0.595 into 10 to the power minus 3 square per second. Okay, therefore factor of safety theta allowed by theta required 0.595 3 1.48 is marginally safe. So for this, see, if the flow rate is high, so geonet is also giving very less factor of safety. What we can do, we can go for some geocomposite or some different things which have higher flow rate, okay, at their pressure. All right. Okay. So with this, we will end today's session. Okay, I just please practice these problems once again, just for your own sake, and so that you just are aware how to what is the difference between transmissibility, permittivity, when is permittivity used, when is transmissibility used, all these things that are clear to you. Anyways, thank you for attending, and in the next session we will be discussing on the erosion control techniques, solve some problems and some other problems also. So see you on the next session. That is, I guess it will be on 10th October. So see you on 10th October, and thank you for attending. Have a good day. So thank you.